The trace function from linear algebra extends to a whole family of functions on groups, and those trace functions on groups are one of the main objects of study of this course. So recall that if we have a matrix A, let's say this is a D by D matrix with entries in F, we define the trace of A to be the sum of the diagonal entries a basic fact about the trace is that we take the trace of a product of matrices. Trace is not a homomorphism. We don't necessarily get trace A times trace B, but we do get trace of B times A. So if we're multiplying square matrices, it doesn't matter what order we multiply them in, we get the same trace. And then a corollary of that fact is that if we have a D by D matrix A and an invertible D by D matrix P, then the trace of PA P inverse equals the trace of A. And that's because the trace of PA P inverse we could write like this. And then this is one matrix times another, so we can switch the order. So AP inverse times P, but that's just trace of A, because the P inverse and P cancel each other out. And then another consequence, well, a consequence of this consequence, is that if we're working over the complex numbers, and A is a matrix that has eigenvalues lambda 1 through lambda d, then the trace of A is equal to the sum of the eigenvalues. And the reason is that since we're working over the complex numbers, then we can write A equals P D P inverse with D a Jordan form matrix. Then D equals P inverse A P. Well, I guess we don't need this because we know that the trace of A is equal to the trace of anything conjugate to it. So we know the trace of A and D are the same. And the trace of D is going to be the sum of the eigenvalues of A which are on the diagonal of D. Now we can't decompose a matrix like this over arbitrary fields, but over the complex numbers we can. So if A is real, this also works. So this allows us to define the trace of a linear operator. So let's say T is an endomorphism of a complex vector space V. We can define the trace of T, well, let's say with eigenvalues lambda 1 through lambda d. We can define the trace of T to be the sum of those eigenvalues, which happens to be the trace of any matrix representing T with respect to any basis of CD, or any basis of V. Now, more generally, the word trace is used to refer to certain functions from a group to the complex numbers. So in particular, we'll call theta a trace function of G, or a G trace, if theta of GH equals theta of HG for all H and G in the group big G. Now, theta could be the trace of a matrix corresponding to group elements, but it doesn't need to be. And again, we don't necessarily have theta of GH equal to theta of G, theta of H. So it's not a homomorphism necessarily from the group to the complex numbers. All we have is this property that theta of GH equals theta of HG. let me use capital, like a script capital T of G, to be the set of G traces. So the set of G traces from G to the complex numbers form a complex vector space. With scalar multiplication defined by C theta is the function that takes G to C times theta of G. And addition is also done in the sort of most obvious way. So theta 1 plus theta 2 is the function that takes G to theta 1 of G plus theta 2 of G. So it's easy to check that the resulting functions are still traces. Now the dimension of this vector space is equal to the number of conjugacy classes in G. And the reason is that, first of all, this has to be constant on conjugacy classes. So if we have theta, a G trace, and we apply it to HGH inverse, the definition of trace is that we can multiply elements in either order. So like we did with matrices, theta of HGH inverse could be written as theta of GH inverse H by grouping these one element and two and then swapping the order. But then that's theta of G. So this has to be constant on conjugacy classes. Now, if G has, let's say, D conjugacy classes, then theta is completely determined by the D numbers, its value in one conjugacy class, its value in another conjugacy class, etc. Let's say x1 through xd, where xi equals theta of g for g in the ith conjugacy class. Let's give a name to the conjugacy classes. If there are, let's say, capital 1 through capital D, sorry, capital C1 through capital CD, then a basis of the trace space is we could look at the functions that evaluate to 1 on each conjugacy class and 0 on the other ones. So let's say psi I of G equals 1 if G belongs to the ith conjugacy class and 0 otherwise. Now, to show that a function is a trace, let's say we have a function theta from G to C. It's sufficient to show that it's constant on conjugacy classes. And that's because if theta of HGH inverse equals theta of G, then theta of GH equals theta of HGH H inverse. I'm conjugating this by H. And then the H and H inverse cancel each other out, and I've got theta of HG. So theta of GH equals theta of HG, just knowing that it's constant on conjugacy classes. So trace functions are sometimes also called class functions, showing one property is equivalent to showing the other. So for example, let's let G be the symmetric group. Let's let theta be the function, let's say the trivial function that sends every element W to 1. Then, well, theta is constant on conjugacy classes because it's constant on the whole group. As another example, we could let theta be the sign of a permutation. So I'll let G be the symmetric group again, and let's let theta be the sign of a permutation, that is -1 to the number of inversions in W. Then if V and W are conjugate, we have that theta V equals theta of UW U inverse for some U. Alright, now you guys probably know that sign is a homomorphism, but I want to not use that property because I don't remember if I really proved it. So let me do this slightly differently using the Brouwer order. So let's write a reduced expression for U, SI1 through SIP. And let's consider, well then, V equals SI1 through SIP, W, SIP through SI1. And we claim that -1 to the length of SIP, W, SIP equals -1 to the length of W. Since SIP is a left and or right descent of W and or a left or right ascent of W, any combination is possible, we have that the length of SIP, W, SIP which is the height above E in the Brouwer order, must be either length of W if we go up and we go down, or if we go down and we go up, or length of W plus 2 if we go up and we go up, or length of W minus 2 if we go down and we go down by multiplying by these generators. In all three cases, -1 to that power equals -1 to the length of W. So if we continue one generator at a time until we get all of the generators on the left and all the generators on the right, then we have -1 to the length of U, W, U inverse equals -1 to the length of W. So therefore this is constant on conjugacy classes. Now it's common to make a group G, let's say there's n elements in the group, into a ring which we write C bracket G and call the group algebra of G. By writing formal complex linear combinations let's say A1 G1 plus A2 G2, etc. and multiplying in the natural way. So I'm thinking of A1 through AN as complex numbers here. And I guess we add in the natural way too. For example, let's look at the group algebra of S3. If we have E plus S1 plus E plus S2, then that's 2E plus S1 plus S2. Also, if we multiply E plus S1 times E plus S2 times E plus S1, then we get EEE plus EES1 plus ES2E plus ES2S1 plus S1EE plus S1ES1 plus S1 S2E plus S1 S2 S1, which is, then we just multiply group elements to whatever they turn out to be. E plus S1 plus S2 plus S2 S1 plus S1 plus, this is going to be another E, S1 times S1 is E, plus S1 S2 plus S1 S2 S1. And we can simplify this because we saw two E's. E plus E is 2E. And we also have two S1s. S1 plus S1 is 2S1. And then we have S2, S2 S1, S1 S2, and S1 S2 S1. Now we can extend trace functions linearly to the group algebra by defining, if we have to apply theta to G1 plus C times G2, then that's just theta of G1 plus C theta of G2. So we make each one an additive homomorphism. The traces are not usually multiplicative homomorphisms, although it happened to be in that last example I did. And the trace space of the group algebra of G is just the trace space of G. So we don't get any new functions that way. The end.